So our problem is similar to yesterday's. Yesterday we didn't have this green arrow. So we still have the system, we still want a model. Very often the model it looks very much the same. So much that I don't quite agree with those that say that the model is gray box. The model itself is not gray box. The model itself is not black box. It's actually the techniques that you use to fit the model that should be either gray box or black box. So given a model structure, I can fit it to the data just looking at the data, or I can fit it to the data looking at the data plus something else. And the plus something else is this green arrow, which is additional information that also comes from the system. It relates to the system. And therefore, it makes sense to use it to build the model. Okay? So when we try to find this model, to approximate this system from two different sets of data, and we want to fit those two sets of data simultaneously, then we refer the problem as a problem of gray box modeling. Okay? So the first great question is, what kind of information is useful? You can know a lot of things about your system, and these informations is probably not useful. So you have a system and you say, okay, this system, or suppose it's a machine, you say, this machine is manufactured by this company. That is information. It's not in your dynamical data, but it doesn't really help you to build a model. Okay? So it's not any kind of information that's useful to build models. So a fair question to ask is, what kind of information is useful? We'll see a few. In examples, I'll show you. I'll mention some others that we use, but I'm not going to show them by examples. But you have a fuller list in the preprint I mentioned yesterday. Okay? Okay, now, assuming that this information and M that belongs to this class are compatible, and that's important because I might have information, it would be useful, but I don't know how to relate mathematically the information to the model class. Then, although I do have the information, it's something I don't know how to use. Okay, it's something I cannot put in there. Okay? Let me just make it, let's suppose you have a very complicated nonlinear structure, okay, that you want to fit to data. And suppose you know that your system is stable, open loop stable. That's information. That's useful. So you want your model to be open loop stable. Now the question is, unless I know how to impose stability on that mathematical structure, it's useless. It's useless information. It is useful in principle, but it's useless in practice. So unless I can actually relate this information to this model class, I'll have to do black box. So when we go for gray box modeling, we must be able to relate, this kind of information to the model class. That is usually the most difficult part. Once you figure that out, the rest tends to be so much simpler. Okay? Okay, now, once we know how these things are related, then the simpler part is, how can we actually use the information to determine the model? Of course, you remember, we're not using only this, we're using this plus the dynamical data. Well, for linear systems, classic problems, simple to solve, are, for instance, if in the auxiliary information were the DC gain of a system. So it's easy to fit a transfer function to a set of data and impose that the resulting transfer function must have a DC gain of, whatever, 1.2, 5.0, whatever. Okay, that's a simple thing to do. It's very helpful sometimes. Or stability, we can even do that in linear systems. But in nonlinear systems, we have a wider range of possibilities. Let me say that these first two, in principle, could also be solved for linear systems if the static function and steady-state data were very simple. But very often they're not, and then the nonlinear case is very interesting. So let me say that these first two are the ones I'm going to illustrate in my examples. So we're going to assume that we have, for instance, a set of dynamical data that, as we discussed yesterday, are produced and collected during dynamical testing. Okay, so we have these data, we still have these data, but now somebody says, okay, I've got a calibration curve for the system. I have a set, I know how in steady state the two variables, input and output, how they are related. So if you think of a plot, you have something like a calibration curve. And unless this is a straight line that passes at the origin, then you must have a nonlinear model. So this could be an S, like an S-shaped curve, or a parabola, or something which is nonlinear. And you know that your system in steady state has that kind of information. Now, this information might or might not be in your dynamical set of data. If they are, then you stand a good chance of having a fair, good model, you know, just doing black box techniques. But what if this information is not clearly present in the data? And that has a lot to do with the test, the way you collected the data. I'll show you in some examples. Then, well, if it's not there in the dynamical set of data, it must come from somewhere else. And it could come from, for instance, a static test. You know, you take your time, you do a static test on your system, if you can. Or you are able to build this from historical data, as I will show you in the third module. And then you have this information again. You don't and you cannot get rid of your dynamical test, but your dynamical test does not have this information. You have it from another source. So the challenge is how to fuse the two different sources of information into one single challenge of building a model that should, you know, comply with both. Okay? Steady-state data is something close to this. This is an easier way to solve this problem. Other things that we have done, I'll show you an example of hysteresis as well, is, for instance, to guarantee that the system has a certain number or a certain symmetry of fixed points, or we want the flow to be symmetrical. That is useful for a number of reasons in some applications. For instance, we are able to impose certain types of bifurcations to the model. So I say, okay, I want this model to have this bifurcation at this point. Now, if I don't impose that using the eye, the green eye, which is not here, or just using the dynamical data, most likely my model will not have this feature. This has to be imposed, okay? So we learn how to do that, okay? For polynomial models, it's very convenient, because if you recall, most of the normal forms of the bifurcations that we study, you know, fixed point bifurcations, the normal forms are polynomial. So there is a relation between the polynomial models and these normal forms. Now, once you figure this out, the rest is quite easy. Okay, so let's start from the beginning. As you recall, we can represent a Normax model like this. Autoregressive part is here, the exogenous part is here. This is the noise part, which we will not use. This has to do with parameter estimation, unbiased parameter estimation. But once I enter with information from another source, it doesn't really make a lot of sense to ask that my estimator be unbiased, because I'm forcing it to do something else that I wanted to do. So to require that the estimator be unbiased is not really meaningful in the sense of gray box identification. So typically we will not have this part. We'll just have regressors in the output variable, regressors in the input variable. Okay. And apart from that, all the examples I will show you, this function is a polynomial of degree L. We have done this for some other representations like neural networks and radial basis functions for some types of information, and that's possible to do, okay? Okay, first step, we consider this to be a polynomial, and we're going to do this steady state analysis. In steady state analysis, we imagine, of course, this assumes that the system is asymptotically stable in steady state. It means that if I fix the input, eventually the output will also be constant. Now, if input and output are constants, so I can say that all the input measurements, regardless of the lag, is constant, and it will be equal to u bar. And the same for the output for the y. Regardless of the lag, since it's constant, all the lagged values have the same value, and we call that y bar. So if we put these, substitute these into this model, eventually you end up with a very simple equation. And it says that it's a steady state relationship. Now, a key point to understand here is this. This is a dynamical model. This is typically a difference equation, whereas this is an algebraic equation. It's a static relationship. It's not dynamical, okay? Why? Because this is the steady state behavior of the dynamical model. They have to be consistent. And well, in this case, this is a consequence of this. Now, in gray box system identification, we want to do the other way around. We assume we have this, and I want to find a dynamical model that when I do steady state analysis, I come back to this. Okay? That is the challenge, roughly. Okay? So let me start with a motivational example. These are data from a book converter. The book converter is indicated here. We call it a DC-DC converter. So you provide DC voltage at a certain fixed level. In this case, this is 24 volts. And depending on how you switch, you command this switch, which is a MOSFET. Then you have various different DC levels of voltage on the load. Okay? Just details. Here we have a set of data. These are collected. This is the format of the input, which is a voltage applied to the gate of the MOSFET. And this is the voltage that you measure on the load. Okay? Let me mention, this is going to be very crucial. Notice that the voltage is somewhere between 12 and 15 volts. So this system, which is nonlinear not only because of the switch, the MOSFET, but also because of the diode, it has been excited or driven around 12 to 15 volts. Of course, this can be driven anywhere between 0 and 24 volts. So we just have a small window of information from 12 to 15. Okay? Okay, so suppose that we do, I'm going to show you what happens if we do black box modeling. Okay? You can imagine what happens with black box modeling. This was a first solution we found to this problem. When we started thinking of these gray box techniques, this is a paper from 2000, so it's just been a long time by now, almost over 20 years if you think when we first started. And the idea is this. The static relationship of that buck converter is known by theory. If you open a book on power electronics, it will tell you that a buck converter has a certain relationship between the voltage you apply to the switch and the voltage on the load. And it's a simple equation because it's just a line, and it's this dashed line you can see here, okay? Now, the black box models we used to get, they fitted the data very well, but they were unable to work outside the range that goes from 12 to 15. That confirms something that is known about polynomial models. They don't extrapolate very well. They're very poor extrapolators. They do a good job in the region you have the data, which is almost everything we can expect. Out of that, the model performance decays very quickly. Okay? Now, in this first solution, what we did, what is the auxiliary information we used in this case? The shape. So we didn't use this line as such. We just used the idea that it is a line. If it's a line, then you go back to your model and you look at your regressors and you say, okay, if I'm going to fit a line, I don't really need this regressor, this regressor, this regressor, et cetera, et cetera. So in the end, you have a reduced set of regressors which are slightly more consistent with the information that the steady state curve, the calibration curve, if you like, is a line. Okay? That's all we do. Just fiddle about, we just remove regressors from the set of candidates. The result is what you see here, quite a good fit around here, and it starts to get bad, you know, at low voltages of the input, which is high voltages of the output. Remember that our data are somewhere in between 12 and 15, indicated by these two small crosses. Here you see the data fit is very good. That's where you have the data. So actually, we gained a little bit here, and all this part here has come as a benefit of using this idea. One step further, we started to impose that the static curve of the model should remain close to the static curve known by theory. And we started doing this using inequality constraints. So you say, okay, I cannot depart from the known line for more than you decide an epsilon. So you decide an epsilon and you remain close. Okay? So you see, this was the first solution, this is the second one, so much closer. Of course, it costs more. And now we estimate the parameters in such a way that these inequality constraints on the parameters are satisfied. This was 2002, okay? So moving a bit further in time, 2004, then we figured out how to do this, imposing equality constraints, and now you can actually say, I want both the theoretical and the model steady-state curves to coincide, okay? And in fact, they do. So these here you have both. Here they're all together, and they are together with the black box solution. The black box solution is this. So if you fit a black box model and it is, dynamically speaking, is very close to the data. But to the data that we have that are in between 12 and 15. So if you look here, 12 and 15 is more or less this region. And in this region, okay, the fit is quite reasonable. And then you have the other solutions. The first one, 2000, 2002 is here, and the third solution is practically right on top. Okay, so this motivation helps us understand in which situations we would benefit the most from gray box techniques. It's a case, for instance, in which I have information about the system behavior, in this case, static behavior, over a wide range of values, either if I think in terms of the input or the output. However, the dynamical data are confined to a small region. So if I only have dynamical data, I cannot expect my model to behave or to have a good performance beyond this point. And in fact, that's what happens with the black box model. Now, if you have a look here, Using gray-box techniques, in principle, what we did was we really enlarged the validity of the model. We imposed that the model should behave, attention, statically, correctly here and here. If the dynamics of this system change with the operating point, then using static information doesn't help. Okay, you follow me, right? Okay, but in this case, the dynamics are more or less the same, and what changes is the gain. Okay, so let me go through the same problem, but now I'll provide a little bit more of information. It's a small thermal pilot plant, okay? And what we're going to use as auxiliary information is the static curve, just as before, okay? And in this case, I'm going to, instead of going through the shape of the static curve, here we're going to follow something a little bit different, also including the shape. First of all, it's a thermal plant. It has no multi-stability. Given an input, it would always stop at the same point. So I know that that has to do with the number of fixed points, and I know how the number of fixed points is determined by the model, and it basically has to do with the degree of the regressors of the output. So I know that P doesn't have to be greater than 1. So what I do is I go to the pool of candidate terms. When I'm going to build a model, when I'm going to choose the structure, I just go to all the candidates, and I remove every single group, or as I call them, clusters of terms that have P greater than 1. It could be just single output terms, it could be cross terms. If P is greater than 1, I don't have to consider them, I remove them, okay? Also, because the shape of the static curve, of the calibration curve, is like part of the parabola, I don't really need cubic terms in the input. Okay? So I have simplified my problem a lot on the one hand. So if you think in terms of, you know, numerical computation, it's much simpler because I don't have to search among so many models. But more than that, since I have chosen a model structure which is consistent with the information I have, I stand a better chance to get a better model. So it's not just solving a time-consuming problem, which is not so time-consuming. Nowadays, you can do this very quickly. But it is actually the chance to improve getting a good model. So I'll show you models. Here we have a black box model. The colors relate to the term clusters. So in black, we have the linear output cluster, the Y cluster. In blue, the U squared cluster, and in red, the UY cluster, okay? So in steady state, you do steady state analysis of this, you end up with this. I didn't add these numbers just to show you that the three terms, they will boil down into one single term, and then eventually I'll add these three numbers, I'll add these two numbers, and I'll add these two numbers. So basically, this equation has this format in which the capital sigmas are the cluster coefficients. They're just a constant, a number. This is the input in steady state squared. 1 minus a constant, so this is a constant, minus a constant times U bar, which is the input, the constant input. This is the equation of the static function of this dynamical model. Now, if I have a curve, I want to ask this question: how do I find these three constants in such a way that this function fits the curve? So here we have, these are the steady state data. On this axis, we have the input, which actually is power that we send to a heater, and this is temperature. So this is how these things relate to each other in steady state. So if you stop the input at this value, so you expect the system to stop at this temperature after quite a long time, because if you have to wait until the temperature settles, you'll probably have to wait a lot. So to get these data takes a long time. The dynamical data are so much easier to get. It's a shorter test. Okay, using a quasi-Newton method, we fit this model to these data. Actually, we find these three constants, and these three constants are here. Now, since I know that these three constants are the summation of parameters of the model, of the dynamical model, then I have my constraints. And that's how I get constraints for this problem. So the dynamical model in steady state is this static equation. And what do we know? We know that theta 2 plus theta 3 plus theta 7, that's the model, the coefficient of that cluster. It should be 0.0615, which is this number, which was obtained solving a non-convex optimization problem that fit this equation to these data, and so on and so forth concerning the other cluster coefficients. So actually, I can build the constraints in this format, and you remember why. If you don't, I'll remind you very soon. But let me just convince you that those constraints are actually these. So if you take the second, third, and seventh parameter, blue, 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 second, third, seventh, you add them up, you must have 0.0615. Theta 2, theta 3, theta 7 are free as long as they add up to this number. So actually, there are three parameters, you have only 2 degrees of freedom, okay? Then likewise, for the red, 5 and 6, they have to add up to this. And finally, the black, which is the linear cluster, 1 and 4, they have to add up to this number. So constant, it's here. S is a matrix, a constant matrix, and then we have the parameters. So the advantage of writing the constraints in this way is that I have a ready solution, you know, which is the constraint least squares solution. Okay? So this solution will actually fit, will do this. It will find the best theta that minimizes the distance between the dynamical data and the model one-step ahead prediction. So we talked about that yesterday. Constrained to the fact that the thetas we find here must satisfy these equality constraints. And the closed form solution is this. The psi, you remember, is the regressor matrix. It's composed of measurements. So actually, we know everything here. We have the black box least square solution here. The regressor matrix composed of data, measured data. The S is the matrix I showed you previous slide. It just is zeros and ones, okay? And the small c also 3 numbers, okay? So you just do this calculation, you get a new model. Now if you add up, for instance, this number with this number with this number, you get 0. It has 0, no, this is not the one. You get the previous, you get what? You get the blue, right? You get this number, 0.0615. Okay, so the performance is, as expected, the crosses, which is, they fall exactly on top of the measured data. Now, the black box model is the dashed line, which is very close. So, was it worth doing all this? Probably not. But what does it mean that the dashed line is very close to the steady state data? It means that the steady state information concerning the system is well represented in the dynamical data. So when we do black box modeling, the method is able to learn that from this dynamical data, and that's it. So this is a counterexample to the one of the buck observer, the buck converter. The buck converter, we didn't have steady state information well represented in the dynamical data. Here it is. So it doesn't mean that you're supposed to do black box techniques every time, or gray box. So gray box is useful when there is some type of information that you have, and for some reason, you suspect it's not well represented in your dynamical set of data. Okay? So this is not an example in which I would go for the gray box techniques. Okay? Now let's look at this, a similar problem, very similar, but not quite the same. Okay? Now, instead of imposing the entire curve, I want just to impose 1 or 2 points or 3 points on the curve. So actually, my source of steady state of information is the steady state data. So all this goes through the same reasoning. The difference is that instead of writing an equation for the static function of the model, I will just get points on the static curve, and those are represented here. So I assume that apart from the dynamical data, which I do have, I also have steady state data. So these are the values of the input, constant input. The bar on the top indicates that they're constant, and also the corresponding constant output. I call these data Z steady state, size M, just to contrast the dynamical data Z, size N. Okay? Now, our aim is, given these two sets of data, I want to find a model that simultaneously fits both sets of data. Okay? So our example starts with a model structure. So I assume that all those previous steps we mentioned yesterday have been solved. Okay. And now we want to find these parameters in such a way that this structure will fit these two sets of data as well as possible. Now, we're going to take as the steady state data only 2 points from the entire curve. For instance, 0.3 and 0.7. And I still want to use this closed loop, closed form solution. So that means that I must be able to write the constraints in this way. Now this is quite immediate, as you would see. The steady state analysis of the model is this. So I have 2 terms that belong to the Y cluster, 2 terms that belong to the U cluster, and 2 terms that belong to the U squared cluster. Now how do I write the constraints? Well, the constraints are simply written like this. I take the 3rd point, this is the output, which I'm going to read on the vertical axis. I place this number here, I place this number here. And also, the 3rd value, which I read on this axis, I place it here, and the squared value of it here. This is one constraint. And you see it's a linear constraint on the thetas. Likewise for the 7. So actually, I can write these 2 constraints this way. So the small c is y3 bar and y7 bar. And then the s, remember that here I'll have the theta. So theta 1 multiplies y3 bar, so it has to be here. Theta 2 also multiplies y3 bar, it's got to be here. Theta 3 multiplies u3 here. Theta 6 multiplies u3 bar, so it has to be here. 4 and 5 have to multiply u3 bar squared, which show up here. And the same for the 7. Simple. What I'm not showing you here is the final model, which the parameters shake a little bit, but the performance of the resulting model is very much like the one with the crosses here. So what it says is that instead of imposing the full curve, I only have to choose, I got the 1, 2, 3, this is the 1, 6, 4, 5, 6, 7. If I just get these two and impose them, that does the trick. What is the advantage? I don't have to solve the non-convex problem I had to solve in this case. Remember? I had to solve this problem, this non-convex problem. I skipped that. Okay. Of course, here I impose the full curve. There, I just guarantee that the curve will pass through 2 points. It's not as restrictive, but it usually is sufficient to improve the results significantly, depending on the problem. Okay. Let me move to a more difficult problem. Here we're going to consider, this one is purely simulated. So my data producing model is a Hammerstein model. And the static curve of this Hammerstein model is like a dead zone. So here I have U bar, here Y bar. And the relationship between these two variables is something like this, which is typical of a dead zone. So the static nonlinear block is here. And basically what you're seeing here is that this point is 1. So up to 1, the output is 0. Actually, to be consistent with that, this is Z. Okay. And then after this static block, I have a dynamical linear model, which is here, very simple. I use random sequences for the input and for the noise. Here is uniformly distributed. Here is Gaussian distributed. And, well, this is just a typical identification experiment. I produce 500 samples, time samples from this system. I will use the first 300 to compose the dynamical set. I'll save the last 200 to compose the validation set, dynamical set. Okay. And of course, I have, I may or may not imagine that I have this prior knowledge, which is the static function of the system. Okay. So I'm anticipating the results here. This, which is the original, is the dashed line in black. If you just do standard black box identification using polynomial models, what we get is this blue rounded curve. And you understand it has to be curved, simple curve, because it's just a low-order polynomial, so it cannot do anything else. You will never get a discontinuity or something which is not differentiable here using a polynomial model. Okay. But we can do a little bit better, and we get the red, which does have this non-differentiable point, but it's in the wrong place, and this inclination is different than this, the slope are different. And eventually, if we do the right thing, we can, using a polynomial of low order, as a matter of fact, I think it's second order, get these black crosses, which are exactly on top of this function. So how on earth do we do this? Okay. And now, in this case, what we do is actually we think in terms of bifurcations. Okay. If you have ever worked with bifurcations, there is a bifurcation called the transcritical. And it's more or less like this. Suppose this is the bifurcation. It looks like a U, but it's supposed to be a mu. Suppose that is the bifurcation parameter. And I want the bifurcation at 0. So what this bifurcation looks like, it's a fixed point bifurcation. We have two families of fixed points. One which goes along this axis all the time, so it's using this nomenclature, y bar equals 0. And the other one is like this, which is another straight line. And what makes it a bifurcation is that this family of fixed points, or this fixed point, is stable up to this point, and it becomes unstable later. And this one is the other way around. It was unstable for mu under 0, and from here, it's stable. Now, this looks like this. More than that. I only have to approximate straight lines, and I can do that easily with polynomials. But now the philosophy is different. I'm not trying to fit a polynomial, a single polynomial that just go around the corner here. I want one line, another line, and hopefully they will switch stability at the right point. So that is what we did in this work. Actually, this was published in 2014. So making the whole story very short, we end up with a lemma, for instance, and I say that a Normax polynomial model, the degree can be greater than 2, no problem, for which the only non-zero cluster coefficients are these 3. Such a model has the following 2 sets of equilibria. So think of these 2 sets of equilibria. Capital 1 bar equals 0, and capital 2, y2 bar, this is the equation of a line with respect to the input. So here, of course, the bifurcation parameter becomes my input. If this is true, then they intercept at this point. What about stability? I cannot impose that. So if the test is good enough, the stability should be okay. I can test it after I get the model, but I cannot impose it so easily, okay? So if you pay attention here, basically what we have is that I'm able to think in terms of cluster coefficients and therefore relationships between the model parameters and impose constraints in such a way that I get a transcritical bifurcation at a certain point, specified point. Okay? So the examples I showed you, so the black box model is the one that has the blue rounded curve, was here. If I remove this cluster and the constant one, which is here, to be consistent with the lemma, I already get the 2 lines, but in the wrong place. This was in the wrong place, and the inclination was in the wrong place. But actually, I can impose exactly using the lemma, and this is the information that comes from the lemma. Remember that I only had 3 coefficients that could be different from 0. Remember that U2 was not allowed. U2 doesn't show up here. It's not allowed in the model. But for dynamical reasons, the algorithms that choose the regressors, they do choose U2, and they chose 3 terms in U2, almost telling me that it is important to have that kind of regressors in the model. But in order to guarantee this, what I have to do is to make sure that the composite contribution of the three terms in steady state must be 0. So actually this can be imposed in the form of this constraint. And the other two just follow similarly, and you end up doing this as we did before. Nothing to fret about. And the result of this is precisely this black result. Okay? So this is the steady state behavior of this model. A low order, it's as far as dynamical order is concerned, is first order. The degree of nonlinearity is 2. And we get a steady state with just this format. Of course, this follows a totally unconventional way of solving the problem. This is thinking in terms of bifurcation, not just fitting dynamical models to moving data. Okay? Let me finish with this. And if we look at these dynamical indices that we use, you know, like the squared sum of errors from the output and the data. So the black box model is the one with the best performance in what concerns fitting the data, okay? The second one, the red one, is the worst, and this is slightly better than the second, but still worse than the first. But this one has the right shape here in steady state. So again, what is your aim? If all you want to do is predict time series, perhaps just the black box model should be okay. But if you want to do some more refined thing, if you want to do analysis, if you want to think of your problem, also in steady state, then the third model gives you more information, which is consistent to the system. Okay. Okay, I'm coming close to, I think this is my last set. Okay. Just a few more slides, and we'll be over. We want to use auxiliary information in a different way. Okay? We're not going to go for the constrained estimation, which has what we've done so far. Okay? But we're going to do multi-objective optimization, which actually is very interesting. It's a little bit different, and I'll show you the differences. But it's very flexible, and it helps us think of the problem in a different way. Okay, so the first thing is multi-objective optimization deals with a problem in which you want to optimize a certain problem concerning different objectives and not just one. So far, we have done only one objective. The objective was, I want to reduce the difference between the squared errors between the data and the model. Okay? Now here we're going to imagine, okay, if I have two data sets, I can have two objectives. I want to reduce the squared errors with respect to the dynamical data and not impose the steady state information, but rather also fit a model that will try to reduce the difference between the static function of the model and the steady state data. So in fact, it's a relaxed version of the previous problem. And every time we relax, typically we gain something, we lose a little bit, but we gain much. Okay? You're not so strict. Having said that, let me make an important remark. We're speaking of these two sets of data. Okay? And I'm trying to convince you that using the steady state, for instance, or the auxiliary information is beneficial, especially if it's not included or well represented in the dynamical set of data. So far, so good. But since you're going to impose it, it better be true. Because if you're not very sure of your auxiliary information and you impose it to the model, so you're imposing wrong information. You're saying, model, you've got to have this, and that this is wrong. So careful. Okay? This is more relaxed. So even if you're not very sure, if saying, I suspect this information is quite correct, but I'm not so sure. So perhaps you shouldn't impose it. Just present it to the model and say, okay, try to find your way around, try to find a balance. And that's what multi-objective does. So it has two objectives. I'm going to reduce the error between these two things and these two things. Okay? So we write it this way. So suppose we want to find the parameter vector in such a way that we minimize not just one cost function, but imagine the sum, the weights could be different, of a set of cost functions. I'm going to only show you examples, a simple example with two objectives, but of course this could go up to 3, 4. The higher you go, the tougher the problem, but in principle it's there. Okay. So the example which is I'm going to show you is basically this. Here we have the bi-objective optimization problem. One cost function is here, the other cost function is here. This cost function has to do with dynamical data, Z is here, and I want to find theta in such a way that the distance between the model one step ahead predictor is as small as possible, or as close as possible to the dynamical data. So this term is in charge of that. The other objective has to do with steady-state data. That was my choice. So for instance, I have steady-state data, I want to use it, not as before, I don't want to impose it, but I want to use it. So I have this cost function, and again, I want the model steady-state information to be consistent or as consistent as possible to the steady-state data that has been measured. And again, we use the two different weights, and because the weights must add up to 1, so this is just lambda and 1 minus lambda. We end up with one single combined objective, and that gives us a vector of parameters. Of course, this vector of parameters depends on lambda. For each lambda, I'll have a slightly different combination. So follow me. If I use lambda equals to 1, this is the single one, this is 0, and I solve the standard least squares problem. And as I reduce lambda, what it means is that I'm paying less and less attention to this dynamical data in order to pay slightly more attention to the steady-state data. On the other extreme, I have a model which has no dynamics, and it's just looking at the static information, and it will be pretty useless unless the only thing you want is the static curve, which is not the case for us. So somewhere in between the two extremes, you're going to find models that eventually are useful. Now, how to choose these models is another issue. That has to do with system validation. You must know what you expect from your model. You have to take into account your problem, etc. Okay? As far as numerically things go, so you can rewrite the previous problem this way. So you have the lambda here. This is the quadratic cost function involving dynamical data. This is the dynamical data. This is the one step ahead prediction. Here you have 1 minus lambda, and this is the quadratic cost function involving the steady state data, which is y bar. And this is the model steady state output. So we're just comparing these things, squaring them, and that's the composite cost function. This has a closed form solution, which is very, very nice, and it's written here. And the only assumption is that either this matrix or this matrix must be non-singular. But that is more or less basic, okay? Usually, the dynamical will not or cannot be singular. If it's singular, it means that your data are not adequate to fit a dynamical model. So you should go back to your testing. Now, for those of you who have worked a little bit with regularization problems, you will probably see that the second objective here enters the problem as a regularization term. Now, when we do regularization, you know, there is this term and this parameter that people really don't know how to choose. We try a few values and say, okay, this should be okay. In this case, what this is telling us is that steady state information is an interesting way or a viable way of choosing this regularization parameter. Okay? So if we solve this for various values of lambda, typically you get something like this. This is the one step ahead cost function, which is this one. Here we have the cost function that relates to the steady state data. And this is the typical Pareto curve. The Pareto curve says that if you want to improve dynamical performance, you might have to give up steady state performance and the other way around. Okay? So for instance, this model has the best steady state performance and the worst steady state, dynamical performance. And this is the best concerning dynamical performance, the worst concerning steady state. Each one of these circles represents a different vector of parameters, therefore a different model. All of them have the same structure. If you change the structure, you get another curve, which might be up here, down here, it might even cross. Okay, that's another issue. So the question now is, how do you choose among these models? And that's what I said before. It has to do with your problem. It has to do with your objectives. Okay? There are, of course, some results that you can easily find in literature. I have pointed to them in the text. Okay, I think this is my last slide. Yes? And it's just to mention other types of auxiliary information that we have worked with. So, location and symmetry of fixed points. This is closely related to the static curve. The static curve is a continuum of fixed points, which is a function of the input. For a fixed input, you have a set of fixed points. You change the input a little bit, another set of fixed points. And so in the end, what you have is what we call the static curve of the model. Symmetry of the flow. So we can say, I want the resulting flow to be symmetrical. Now, for instance, if your system is known to have a pitchfork bifurcation, then there must be symmetry. And symmetry is something which is not structurally stable. Any small parameter variations will destroy symmetry. So unless you impose symmetry, your symmetry is gone. So that's something important. For a long time, we were unable to reproduce exactly the pitchfork bifurcation. It just becomes a saddle node bifurcation. And the way out was to impose symmetry. And as soon as you impose symmetry, voila, there you have it. Okay? Let me just mention another example, which is more concrete, and it surprised us because it worked quite well. There is, for those who work with time series analysis, there is a benchmark, a famous benchmark, which is the time series of sunspot numbers. Has anybody seen this series before? Sunspot numbers? It's available. It's a very tough series to model. It has been, data has been collected from the 18th century. Of course, the method of collecting, of counting these has changed, so the whole thing is not as long as we would like to. But the series just jumps like this. And to do this with models is very hard. So somebody figured out that if we take one cycle originally and we just flip the other one, so you flip one other cycle, you get a time series which is, you know, it's closer to a sinusoid than just these bumps. And this one is also easier it's much easier to model, but it has discontinuity problems somewhere close to the origin. So my colleague, who is a topologist and, you know, knows these things very well, he said, okay, we're going to do this. We're going to get the original sunspot series. We're going to map this into a symmetrical space, a space that is symmetrical by construction. Okay? And since we know how to guarantee symmetry of the flow by gray box techniques, then we stand a much better chance of getting a good model. And in fact, we did get a nice model. Okay? This has been published in 2006, 2008. So it's a very nice, interesting application. It was surprising. Okay? Then I saw other people using these ideas, for instance, to design models for antennas, and antennas are symmetrical. So there are many examples in which symmetry is important to be taken into account. So as far for bifurcations, we have been able to do this with 3 different types of bifurcations. The flip, the transcritical, which I just mentioned here. The hop actually is not the hop, is the Neimer-Sacker, because we did this for maps. Okay? Hysteresis, and I'm going to start the next module with this example. And this is ongoing research, okay? Now, let me just mention that all of this has been done for polynomials, and some of this has been done for MLP networks and RBF networks, okay? So, as promised, I was shorter today. And I'm available for questions if you have any. Any questions? Thank you very much. Any questions?
Well, thank you very much, Giri. It was a very nice talk. Well, you mentioned that sometimes it's very useful to impose symmetry.
Yeah.
On the other hand, if we're dealing with experimental data, sometimes even if your problem seems to be a symmetric one, if you have, for example, imperfection sensitivity in Euler buckling, you look at your system, it seems to be symmetric. If you impose symmetry, you are not going to have good results, because saddle node is actually the phenomenon that matters, not pitchfork bifurcation. So I think that before you impose something, you have to be very sure that the physical phenomena is not going to be missed somehow. Well,
exactly, that's exactly the point. You must be sure, otherwise you're imposing something wrong. Okay? The one thing is, okay, do I want to learn what the system is? Okay? So if you want to learn what the system is, you want to learn what the system is with all its features and imperfections. So then that's the time to use black box, of course, as long as your data is good. But suppose you have a system, but in that case, it's like the antennas and all these things that they're supposed to be symmetrical. Or the other problem in which you map the system to a symmetrical space by design. I mean, you choose this to be symmetrical, and you work here because you know how to guarantee symmetry. Then you come back. So you benefit from symmetry in this fake symmetrical space, which you take your data this way. You work here, you benefit from knowing that here things are symmetrical, and then you go back. Of course, it's not the case you mentioned. Okay, but your example is the perfect example of a situation in which, unless you are totally sure, then you shouldn't do it. Or then, you can try to use some kind of by objective identification in which one goal is to become symmetrical, but then you just don't quite be symmetrical. You just give up symmetry gradually, and you improve the other side. And then you have models that are gradually more and more or less and less symmetrical. And then you say, okay, this is the best point to be. And then you have an information about your system. But you're totally correct. Any other question before the coffee break? Okay, so then I'll see you after the coffee break for the last module.